Now, in order to describe situations with all of these, what we do is we have a tool that we use from now until the rest of the year is over, and that's what's known as force diagrams. Force diagrams have two things. They have one, a rough picture of what's going on. And number two, all forces on the object drawn from the center. Anytime we deal with forces in this chapter, you will need to have a force diagram drawn correctly, and that will probably be that, along with other givens in the situation, will be probably half your points. Not probably, it will be. I know that. I shouldn't say probably when I know it's the case. It will be half your points because it is very imperative to figure the problem. So let's start with some of them, some basic ones right now. Yes?
Are those kind of like how we drew the little pictures, like they help us? Or are they part of the actual problem?
Both. I mean, I'll grade it on there. It's so imperative for you to do it, to do the problem right. That's why I require it on your problems. I mean, I think you guys saw from kinematics that the reason why I was so worried about the picture and the given and the find is if you did the picture and given and find 100% correctly, the rest of the problem became easier. Like a lot of times I would actually do the picture and the given and find, and once that was over, you're like, I know exactly how to solve the problem now. It was that's the physics portion. Everything beyond that is very typically the math. And so that's why it's so imperative here. All right, so let's do some basic ones here. Let's say I have a car just sitting there. Sitting. Settled. Sitting. There we go. So I've drawn the picture. Now help me out with the forces. What forces are acting on here? Gravity, of course. So I'll draw from the very center. Draw that straight down and label it FG. Small little hint with force diagrams to help you out. When the forces are balanced, you'll find that it's always at a very constant speed. When the forces are unbalanced, you'll find that it's changing its speed or accelerating. So that kind of helps you to figure out whether or not they need to have other forces there. So this obviously is staying at a constant speed. So where are we probably going to have a force? Which direction? What are we left with? Is it balanced now? No? Where does it need to go in order to be balanced? Up, right. What would be the force that would be pushing this object up if it were just sitting there? Electromagnetism, but what will we specifically say? We're not going to say electromagnetism because... Normal. There you go. I'm going to do two more and then we'll be done. All right, what if we just step on the gas, but we're going to slow speed?
Friction.
We will have, yes, we will have friction, absolutely. Which way will it go?
That way.
Yep, because the speed's this way. You can see it on lines. All right, and let's see, it's not going to be very big at all. Why is it not going to be very big? It's going slow. I'm not running into that many atoms. What else do we have? Oh, I'm sorry. No? Better?
Yeah.
All right. What else do we need?
Gravity.
Gravity, absolutely, and it's going to be exactly the same. Real quick side point, remember that gravity, all these forces are vectors. So the size, the length of the vector is a direct effect on the magnitude. So if I drew a person next to here and wanted to be accurate, how would their force of gravity compare? Oh, it would not be the same, no. The force of gravity, how would it compare? What's that? Would the weight of the car and the force of gravity on the car and the force of gravity on the person be the same? No, why? Different mass, right. The car has more mass and therefore has more force of gravity. Yes?
Okay, so would the friction be going that way because the car is going that way?
Very good. Remember we said right over here that force of friction always goes the opposite direction of velocity. Because if you're running into all these air particles, which way are they going to push you with their electrons? Back the other way. If I jump up, they'll push me down. If I fall down, they'll push me up. Yes.
So you said that on the one of the car was sitting, and it had like the force normal to balance it out.
Right.
So on the one that's going, does the force friction and the force gravity balance each other out?
No, force normal will balance each other out. When I say balanced, it needs to be in that particular direction. The Earth is still pushing the car up the exact same amount. Yes? Force normal is what we talked about just before when we said there's a solid object right here. Everything on this desk has gravity pulling it down, right? Why is it not going? What's that? Because of the surface. The what in the surface? The electrons in the surface are pushing on the electrons of every single object here, right? And pushing them up. That's what we define as force normal.
Okay, but
When you have a solid object. So the table's pushing up. If I run into the door, that'd be force normal back. If I run into the ceiling, that would be force normal down.
Force normal is going up because the car is sitting on the ground.
Very good, yeah. Okay. And we have one more force here. What is it?
Let's go that way.
It does have to go that way, but it's not balanced. How come? Not because I'm not because moving. What did I say? Remember I said, they're balanced when you're at a constant velocity. The force diagram, and notice that I'm saying this very clearly, so... Okay. The force diagram does not show the direction of motion. It shows the direction of acceleration. There are no velocity vectors up here whatsoever.
It doesn't show what.
It does not show the direction of motion, or I should specifically say, it does not show the direction of velocity. It shows the direction of acceleration.
what does?
The force diagrams.
Ah.
So here, you'd see that there is no acceleration, because it's balanced out. Here, what's going to be the direction of my acceleration? Would be, yeah, well, to the right here, absolutely. Yes?
How do you know, like, how long to make the arrows?
I'm just roughly guessing. The only thing that I'm doing to compare it is making one bigger than the other. The reason I knew that that was bigger is because we stepped on the gas at slow speeds. We're probably going to be accelerating. Okay? On the other hand, last one we'll do, and you guys can take your 5 minutes. What if I was at cruise control?
What's your speed?
It doesn't matter. We'll go 60 miles per hour.
So it's close.
Well, cruise control, yeah, probably. Unless you have a faulty cruise control. In which case, I wouldn't suggest using it.
I use it every morning.
There you go. I imagine because it stays at the same speed. All right. So what forces are on it now? Knock the two easy ones out of the way real quick. Come on.
Gravity.
Gravity and normal. Absolutely.
So is everything going to have gravity?
Everything will have gravity when it's where? Earth. Everything will have normal so long as it's... What's that? No.
Touching the surface.
Touching the surface. Right. So right now, does this have force normal? Until when?
It's on the ground.
No, not until it's on
And
the
it's like floating.
I wish I wouldn't have done that. All right. Until it's not being pushed up by the table anymore. And at that time, did it accelerate? Yes, it did. All right, final ones here. We should have force friction back. I drew it bigger. How come?
It's balanced.
Not because of constant velocity.
This is going faster.
Because you're going faster. Very good. So you're running into more air, right? The more air I run into, the more it's going to push me back. And I put a force applied forward.